welcome to our third video in the sequences series. This one's geometric sequences, so we're going to introduce those and discuss an example of compound interest as well. So a geometric sequence is a sequence where each subsequent term is found by multiplying the previous term by a fixed amount, i.e. r. So we've got t at n is equal to r times the previous t n minus 1. For example, 2, 6, 18, and 54 is a geometric sequence where it's multiplying by 3 each time. The nth term of a geometric sequence is given by t at n equals a, the first term, times r, the common ratio, to the power of n minus 1. An example, these are from the book. So example 18, find the 10th term of the sequence 2, 6, 18. So if we look at our first variables, we've got our a, the starting term is 2, r is 3 because it times by 3 to get to 6 and 3 to get to 18. And so our t at n is equal to 2 times 3 to the power n minus 1. We then chuck in our values of 10 for n to get 2 times 3 to the 9. Chuck that in your calculator, 39,366. For our geometric sequence, the first term is 18 and the fourth term is 144. Find the common ratio. So it gives you A and it gives you T4 or T1 and T4. So again, we're starting with what we know. We know T4 is equal to 18 or to A times R to the 3, which is 144. We then divide by 18 to get r cubed is equal to 144 on 18 equals 8, which is conveniently the same as 2 to the power 3. So r to the 3 is the same as 2 to the 3, so r is equal to 2. The third term of a geometric sequence is 10 and the sixth term is 80. Find the common ratio and the first term. Again, starting with what we know. We know that T3 is equal to A times R squared, because n minus 1, 3 minus 1 is 2, and that's equal to 10. T6 is equal to A times R to the 5, and that's equal to 80. A simple way to get rid of the A is to divide T6 by T3. AR5 divided by AR2 is R cubed. 80 divided by 10 is 8, or 2 cubed once again. Therefore, r is equal to 2. We keep moving down. We can then use that r2 and our t3 to find what a is. So t3 is a times 2 squared equals 10. So a is going to be 10 divided by 2 squared, or 4, equals 2.5. All of these can be done on your calculators, particularly these ones when you have something that is not obviously a number to the power of 3. You can use the solve function. Quite simply solve r cubed equals 144. Well, sorry, x cubed equals 144 because it doesn't like r's, but yeah. That's 2. All right, compound interest. First, we need to remember that compound interest is interest calculated at regular intervals on an initial amount and any accumulated interest between. So we start with $1,000. If it's compounding annually with a 10% interest, the second year it will have an extra 10% of that $1,000, or 110% of the original amount, the original 1,000, or 1.1 times 1,000. 1.1 just being our decimal form of the percentage, and that's equal to 1,100. At the end of the second year, or the next year, it will grow by another 10%, but that 10% will apply to both parts. So 10%, so 1,100 plus 10% of 1,100, or 1,000 plus 10% times 100 plus 10% of that entire amount. And that's 1.1 times the 1,100, or 1.1 times 1.1 times the original 1,000, 1.1 squared times 1,000, therefore showing you that it's going up 1.1 times each time. It's a geometric sequence where r is 1.1 and a is 1,000, similar to that. So our example from the book, Marta invests $2,500 at 7% per annum compounded annually. Find the value of her investment after 5 years and how long it takes until her investment is worth $10,000. Start with what we know. We know A is going to be equal to 2,500 and R is going to be that extra 7%, so 1.07. We can plug those in, so T at N equals 2,500 times 1.07 to the power N minus 1. After 5 years, T5, 2,500 times 1.07 to the power 4. In your calculator, 3,276.99 or 99 cents. B is a bit more complex. I've got two solutions in here. We'll go through, both needing your calculator at one point. So T to the N is equal to 2,500 times 1.07, N minus 1 equals to 10,000, or it's actually less, greater than or equal to 10,000. We then divide by 2,500, 1.07 to the power N minus 1 is equal to 4. It's at this point you actually need to use your calculator, because again, it's one of those weird numbers that you're not going to know what 1.707 to the power of N minus 1 is in terms of 4. So I'll just chuck it in. Solve 1.07 to the power x minus 1 equals 4. And we get x equals to 21.489, etc. This means as it's compounded annually, that it won't be until x is 22 that it's above 10,000, because 21 will be below. So by the end of the 21st year, i.e. when x is 22, the investment will be over $10,000. The alternative one is that we use our sequences section of our calculator, use our explicit definition, as that's the one with the n terms, 2,500 times 1.07 to the power n minus 1. Look at our results until we see one that has 10,000 in it. Oops, my thing's moved. There you go. Note 22 is at the end of the 21st year. So by the end of the 21st year, the investment will be over 10,000. This way is a lot faster, but it's a lot easier to screw up. This way, I can show you some more maths. Hope you've enjoyed that. I'll see you another time.